before you watch this lesson, go back, if you haven't already, and complete the Can This Date Be Salvaged? It goes along kind of with the Pepe and Pia at their Starbucks, trying to meet at Starbucks. So just pause and then go back and do it, and then come back to the lesson. So you already have completed that side. You can see that we can patch holes whenever the limit exists. So on this first one, we would just need to go back and make sure that, so we want f of negative 1 to equal the limit as x approaches negative 1 of f of x. So we could just go back and say that f of negative 1 is 1, and then that would just fill that hole. Okay. So in this one, you graph the function for all the x values except 3. You're going to square the x, subtract 5. When x is 3, the point is at 2. And so if we wanted to patch the hole, we would just take that point and move it up to 4. So instead of a 2 there, you would have a 4 there. All right, so on 3, the domain, x cannot be negative 5. If we put negative 5 in, we end up with 0 over 0. So for a rational function, which is a function that has a polynomial on the numerator and a polynomial on the denominator, when you get 0 over 0, that means there's a hole in the graph there. So what I did on C is I wrote it as a limit. I went ahead and factored. The x plus 5s would cancel out. And I'm left with negative 10 for that limit. So that means that for the function to be continuous, that h of negative 5 would have to equal that negative 10, and that would fill the hole, or patch the hole. All right, so for our notes, we're going to be removing discontinuities. So we're going to be patching holes. So discontinuities that occur where a limit exists can be removed. And that's the case when you have removable point discontinuity by defining or redefining a point on the graph, or patching the hole. All right, so there's two things we need to do. We need to evaluate the limit as x approaches whatever value of f of x. Where that limit doesn't exist, we can't remove the discontinuity. If it does exist, we're going to define f of a to be whatever you got when you took the limit. All right, so let's look at number 1. We're going to determine what points could be added that would make this function continuous, or explain why that's not possible. All right, so let's start with our first place of discontinuity, which is when x is 1. Now what we could do is take this point right here, that's at 1, 2, and redefine it. That to 1, 1. Okay. Our next point of discontinuity is when x is 3. Now this type of discontinuity, the limit doesn't exist. because the limit as x approaches 3 from the left is going to be 1, and the limit as x approaches 3 from the right is going to be 2. So that cannot be patched or removed. Because it's non-removable jump discontinuity. So there's nothing we can do there. Okay. So the next place where we have discontinuity is when x is 5. Okay. So since that is removable point discontinuity, we just have a hole there, and the function is completely undefined at x equals 5. So we'll just define a point at 5, -1. Okay, and then our last point is going to be where x is 6. So you guys try this one on your own. So the function is completely undefined when x is 6. So we would just define a point, and to patch the hole or to fill the hole, that point is going to be at 6, 1/2. So that's not too bad. All right, so let's look at the next one. So you see a lot of piecewise functions on these types of problems. So 2 says, what value of k would make h of x continuous? And then we're going to use the definition of continuity to justify our choice. All right, so first, let's just go ahead and see if we can do it by finding the limit as x approaches 9 of h of x. And because that is a rational function, I'm just going to go ahead and factor. Right. Now the x minus 9s will cancel, so then I can take 9 and plug it in for the 2. I'm sorry, plug it in for the x, and I get that the limit as x approaches 9 is 11. So for this to be continuous, then we would need for h of 9 to equal 11. And the way for that to happen is for k to be 11. Right. So the definition of continuity, we would say that the limit as x approaches 9 from the left of h of x equals the limit as x approaches 9 from the right of h of x. Because from the left and from the right of 9, we're just using this function right here. And both of those equal 11. We found that. And then when we redefined k, h of 9 is also equal to 11. All right, and then for example 3, the piecewise function f of x is given below. Find the values of a and b that make f of x continuous. Okay, so let's just start with 0. So there's 3 pieces here. We have a piece ending and starting at 0, and then a piece ending and starting at 5. So we're going to start with working with the 0. And so what we need for this function to be continuous is for the limit as x approaches 0 from the left of f of x to equal the limit as x approaches 0 from the right of f of x. All right, so from the left, our function is just equal to 2, so I know that limit is going to be 2. And then from the right, I'm going to take 0. I'm going to plug it in for x. All right, and then solve that for b. And so I know that b is 2, so that's great. I can just go ahead and come up here and mark b out and make it a 2, and then use that when I go to do the second part of this problem. All right, so for the 5, dealing with the 5, we need the limit as x approaches 5 from the left of f of x to equal the limit as x approaches 5 from the right of f of x. Right. And to find this, we're going to take 5 and plug them in for x. Now I know b is 2, so I just went ahead and used 2. All right, so that's going to give us 5a plus 2 is equal to negative 8. All right, and then we'll just solve that real quick. And we're going to get that a is negative 2. All right, so those are the values of a and b that make that function continuous. A, negative 2, b, 2. Okay, so I'm going to do one on your homework sheet. So grab your homework sheet real quick. This is one that's a little bit more challenging than the one we just did. It looks similar, but to actually do the solving, it's challenging, and it's using some things you haven't really used since Algebra 2. All right, so we want to determine the values of m and k so the function is continuous everywhere. So very, very similar to what we just did. But like I said, the solving part is going to be more difficult. So let's start with the negative 2. So we need the limit as x approaches negative 2 from the left of g of x to equal the limit as x approaches negative 2 from the right of g of x. Right, so same thing we just did, take that negative 2, plug it in for x. All right, so negative 2 squared is 4, so we get 4k plus m, and then that's going to be negative 7. So this is different. It didn't work out nicely like last time where you're just left with b equals 2 or whatever. So we're not quite done with that one. So we're going to go ahead and look at the other one real quick. So the other limits we're worrying about are when x is 3. So we need for the limit as x approaches 3 from the left of g of x to equal the limit as x approaches 3 from the right of g of x. So we will plug in 3. All right, so it looks like over here we're going to get 13 equals 3k minus m. All right, now this takes us to something we haven't done in a while, but we have 2 equations with the same 2 variables. We're going to solve this. It's called a system of equations, and we're going to solve it. And I think we're going to just do the elimination method. So I'll take this one and bring it over. All right, and then bring this one. It doesn't matter what order you write them in, just line up the like terms. All right, and so because my m's are already opposites, if I just add these equations together, the m's will be eliminated. And we know that k needs to be 6/7. Right. And then we can take that k and plug it into either equation, the green one or the purple one. I'm just going to choose the green one for no specific reason, except the m is positive, so it's like one less step. All right, so that's going to be 4 times 6/7 plus m equals negative 7. All right, 24 sevenths plus m equals negative 7. All right, we'll subtract that fraction, which is not super fun, but it's not too terrible. So I know that, oh, I don't know why I changed that to fourths. Let me fix it real quick. I need negative 7 to also be sevenths. So that's going to be negative 49 sevenths minus 24 sevenths is going to give us negative 73 sevenths for m. Okay. Sometimes you may have to solve a system of equations, and elimination is, to me, definitely easier on this one. You could go back and do substitution if you wanted to also. Okay, so your assignment is to do the 5 problems that are left on this worksheet, and I'll see you guys next week.